Good afternoon, everyone. This is lesson 2.3, dealing with Newton's second law of motion. It's from the Dynamics and Gravitation unit of Physics 20, which is Unit 2. And for you West Country Outreach students, we're going to be looking at, I believe it's page 8 of your unit handout. What are we doing today? We're going to be looking at describing Newton's second law of motion and applying Newton's second law of motion to what I would describe to you as very basic situations. This is a very important law of motion, Newton's second law of motion, and it turns out that we're going to be applying Newton's second law of motion to a number of different situations over the next, I would say, 4 or 5 lessons. And then in Unit 3, when we talk about circular motion, or what we refer to as centripetal motion, Newton's second law of motion is going to make its appearance again. So the applications we're looking at today are very, very simple, and they will progressively get more and more difficult as we go throughout the course. Before we start with this lesson, I want to review Newton's first law of motion. And this goes back to the very first lesson in this unit, where I probably told you in junior high science, or maybe even in Science 10, you might have been told that Newton's first law of motion says an object at rest remains at rest, or an object in motion remains in motion unless acted on by some outside external force. And we cleaned that up a bit, and we wanted to make it more useful. So Newton's first law of motion says if the forces acting on a mass are balanced, then the velocity does not change. What does that mean, to say the forces are balanced? It means that there may be forces acting on the object, but they are canceled out by equal but opposite forces. If you imagine what's going on with a textbook sitting on a tabletop, there is a force of gravity pulling the textbook towards the center of the earth, but the table is pushing the textbook back, resulting in a net vertical force of 0. So that's what I mean by the forces acting on the mass are balanced. When I say if the forces acting on the mass are balanced and the velocity does not change, that covers situations where the object is at rest, and it covers situations where an object is moving at a constant speed in a straight line, because velocity is how fast and in what direction. So if the velocity doesn't change, the speed doesn't change, and the direction doesn't change. Well, what's another way we can say the forces acting on the mass are balanced? We can say the net force acting on the mass is 0. So all I've done is I've tweaked that statement to now read if the net force on a mass is 0, then the velocity does not change. Well, what's a more succinct way of saying the velocity of something does not change? It's to say that the acceleration is 0. And acceleration is the rate at which velocity changes. So if I say the velocity is not changing, then the acceleration is equal to 0. So that third line is what Newton's first law says about balanced forces. If the net force acting on a mass is 0, the acceleration is 0. The other side of that coin was we said if the forces acting on a mass are unbalanced, then the velocity will change. Now, what does that mean? It means that if the forces acting on the mass are unbalanced, then the mass may be speeding up as a result of that, or it may be slowing down as a result of that. But it's also possible that it could be just changing direction as a result of that, because the velocity is how fast and in what direction. I just really want to stress that when we say a velocity is changing, all we know is its speed is changing and or its direction is changing. Well, we've already established that when the forces are balanced, we can say the net force is 0, and that means when the forces acting on a mass are not balanced, the net force is not 0. And whenever students see that not equal to 0 thing, my recommendation to them is to think about what that means. If I say the net force acting on the mass is not 0, it's telling you it's some other number. It's telling you maybe the net force is 100 newtons south. But if there is a net force because it's not zero. Then the velocity changes, but that means if the net force is not zero, the acceleration is not zero. And that last statement is one that I think you really have to stop and think about. What is it saying? It's saying if there is a net force, there is an acceleration. Above, the third line from the top says if the net force is zero, the acceleration is zero. That's just saying if net force is zero, acceleration is zero. The bottom line is saying if the net force is not zero, the acceleration is not zero. If there is a net force, there is an acceleration. So that takes us to Newton's second law of motion. And for about the next 5 minutes or so, I'm going to be flipping through these. I'm not going to be rushing through them, but I'm not going to be taking my time, so you know the drill. If you need to pause it to write some things down or some ideas down, by all means do so. A net force acts south on a small car that is moving south. What effect does this have on the car's motion? Well, there's a car. You can draw a car if you want to. You can draw a block of wood if you want to. It doesn't matter, but there's a car, and I'm assuming it's in gear and it's moving south. No driver, unfortunately, but it is moving to the south, and we're saying that there is a net force acting on the car. Well, if there is a net force, then the forces are not balanced. Because if they were balanced, we would have no total net force. So if there is a net force, the forces are unbalanced, that means there is an acceleration. So what effect does this force that's south acting on a car that's moving south have? What effect it has is it provides an acceleration to the car. The car will experience an acceleration. And if you want to get specific, the direction of the acceleration will be south. And if you want to be even more specific, since the car is already moving south, it will be speeding up, but that's not the point of this warm-up exercise. The point is there's an acceleration because there's a net force. The next question says we take that same net force that was acting on that car, and it was acting south, and we apply that same net force to a large truck that's also moving south on the highway. The question is, what effect does this have on the truck's motion in relation to the effect it had on the car's motion? Well, here's the car. I'm just going to bring it back. You don't have to. There's the net force, and there's the resulting acceleration. So now we take a look at a truck, and the truck is larger. I'm just going to interject here to clear something up. I just said that the truck is larger. What my intention is in saying that is that the truck is more massive. And looking at these two little pictures that I clipped in here, it's not entirely clear that that red truck is more massive than the Jeep. So just imagine that the bed of the truck is filled with sand or something very heavy. The intent of all of these images of the red truck is that the red truck is definitely more massive than the Jeep. And I admit we have to rely on a bit of intuition here, but I don't think we've gotten to this stage in our lives without knowing how forces interacting with objects operate. Intuitively speaking, if you apply that same net force to the truck, since the truck is larger, or better yet, more massive, it will accelerate because there's a net force, but the amount of the acceleration will be less. You know, unfortunately, teaching this way through video and at a distance has its disadvantages, of course. If I were in front of you right now, I could get out a couple of different cars, little mini cars, one being a car, one being a truck. We could put them on the same surface, and we could apply the same force to each of them and observe what happens, and the car would be winning the race. The car is going to accelerate at a greater rate because it's less massive. So both will experience an acceleration towards the south. However, the car's acceleration will be larger than the truck's acceleration, or the truck's acceleration will be less. This becomes really apparent if you imagine you're sitting at an intersection in your vehicle, and beside you is a very large truck-trailer system. When the light turns green and you both hit the gas, you accelerate very rapidly compared to that truck-trailer. Number 3, what effect would a larger net force have on the car in number 1 above? Or a smaller force? Well, I'm just going to deal with the larger force. Here is the original situation with that car. It's a little Jeep of some kind. There's a net force. There's an acceleration. There is the same vehicle, because it says same car, and I'm going to apply a larger net force. Again, common sense dictates what we know is going to happen here. When you apply a larger force and it results in a larger net force acting on an object, what you end up getting is a larger acceleration. So how would this be accomplished with two identical cars sitting at the lights when the light turns green? Well, one of the drivers just pushes down on the gas pedal a little bit, applying a forward force to the car. The other driver pushes the pedal to the floor, applying a larger force. And we know, of course, when you push the pedal to the floor, producing a larger force, you accelerate at a greater rate. So what we learn from this is a larger net force will result in a greater acceleration for a fixed mass. And I guess I haven't really answered the second part of this, what if it were a smaller force? I think it's obvious, and you can write it down if you like, that a smaller net force will result in a smaller acceleration. So now we want to talk about the relationship between the net force that is acting on an object and its acceleration. And in science, it's important that whenever you talk about a relationship between two variables, you keep everything else constant. If I want to understand the relationship between temperature of wash water in my washing machine and cleanliness of clothes, I need to make sure that I do an experiment where I'm washing the same clothes and I'm using the same type of detergent. Because if I start to change those variables and I use a t-shirt that's got grass stains on it in one situation and I use a t-shirt that's got mud on it in another, I won't know why the t-shirt gets cleaner in one situation than the other. Was it because of the temperature of the water? Was it because it was just soiled in a different manner? So my point here is the relationship between net force and acceleration is one where we want to compare the same mass. So what we discovered here was when you have the same mass but a larger net force, you get a larger acceleration. The acceleration depends on the net force, and if you want to look at it graphically, which is what we're going to try to do in a lot of our analyses in high school physics, the acceleration depends on the force, so the acceleration is the dependent variable that goes on the vertical axis, and it's this type of relationship. It's a linear relationship where if you applied twice the net force, you would get twice the acceleration. And that is called a direct proportionality. And it means exactly what I just said. If you apply twice the force, you get twice the acceleration. If you apply 5 times the force, you get 5 times the acceleration. If you apply only 1/3 of the force, you will only get 1/3 of the acceleration. And number 5, we want to describe the relationship between the mass and its acceleration caused by a net force. Well, here we have to, if we want the relationship between mass and acceleration, we have to keep everything else the same. So we want to make sure that the force is the same. I apply that force to the smaller vehicle. I apply the same force to a larger vehicle with more mass. And I see that what happens is as the mass increased from the car to the truck, the acceleration decreased. What that's going to look like, and again, the acceleration here depends on something, it depends on the mass, is it looks like this. And this is a very important mathematical graph or relationship in physics. This is what we typically call an inverse proportionality. And I It is an inverse proportionality. I wish they would have called it a reciprocal proportionality, but that's okay. You will see it as inverse proportionality whenever it's talked about in physics and science. And all this is saying is as the mass gets larger and larger, for a given force, the acceleration decreases. And if the mass were smaller and smaller, for a given force, the acceleration would increase. So what we are saying is that the acceleration is inversely proportional to the mass, but we are also saying the acceleration is directly proportional to the force. And that's Newton's second law. Newton's second law on your formula sheet looks like that. It says the acceleration is directly proportional to the force and inversely proportional to the mass. And although that's how it appears on your formula sheet, 99 times out of 100, I will write it this way, and you will probably get accustomed to writing it this way, that the net force is equal to the mass times the acceleration. And I guess just the point I'm making here is it's net force we're talking about. It drives me a little batty when I see people write F equals MA. It's not F equals MA, it's F net equals MA. You want to be very careful about that moving forward. All right, example 1, what happens to the acceleration of an object if the mass and the net force both decrease by a factor of 4? Well, the acceleration, I'm going to go with magnitude of the acceleration, is equal to the magnitude of the net force divided by the mass. So what this is saying is the acceleration is proportional to the net force, and the acceleration, this is how we're going to write it, is inversely proportional to the mass. What this first statement says, the one that I'm going to highlight in yellow, is whatever change occurs to the force, the acceleration will experience the same change. So if I decrease the force by a factor of 4, and I'd like to write that down so you know exactly what that means. If I take the magnitude of the force and I multiply it by 1/4, what does that do to the acceleration? Well, the acceleration will also be multiplied by 1/4. This results in the acceleration being multiplied by 1/4. Well, that's one of the changes that occurs. It says, however, that the mass is also decreased by a factor of 4. So the mass is multiplied by 1/4. What does that mean? Well, now we're going to look at the statement that I'm highlighting in blue. What happens to the acceleration is the inverse, or kind of the opposite, of what happens to the mass. If the mass gets multiplied by 1/4, then the acceleration will be multiplied by 4, the reciprocal of 1/4. In other words, if the mass gets smaller, the acceleration gets larger. And when we put these two things together, if I take the acceleration and I multiply it by 1/4, and then I multiply it by 4, I'm left with the original acceleration. So the answer to this question is nothing. Nothing happens to the acceleration if I reduce the force by a factor of 4 and then reduce the mass by a factor of 4. The acceleration will be the same. There is another way to look at it, and as we get further into the course, and particularly in Physics 30, there are going to be a variety of different ways that we can analyze these types of questions. The other way that you can look at it is to say, well, I'm multiplying the net force by 1/4, and I'm multiplying the mass by 1/4, and these two things that I'm doing cancel each other out, so there's no change. I'd be very hesitant in using that method all the time. It's going to get trickier than that. Both the mass and the net force increase by a factor of 4. Well, let me try this in a slightly different way. If the mass is increased by a factor of 4, intuitively speaking, it will only experience 1/4 the acceleration. More massive objects accelerate less. On the other hand, if I increase the net force by a factor of 4, that would normally result in 4 times the acceleration. So on the one hand, the larger mass reduces the acceleration by a factor of 4, and the larger force increases the acceleration by a factor of 4. Once again, there will be no change here. The mass increases by a factor of 4. Well, that will mean the acceleration is reduced by a factor of 4 or multiplied by 1/4. The net force decreases by the same factor. Well, whatever happens to the force happens to the acceleration. So that means that the acceleration will be multiplied by 1/16 of the old acceleration. This is the new acceleration, and it's 1/16 of the old acceleration. Just to give you a strategy to use here, I suppose what you could do is you could take a mass of 3 kilograms and a net force whose magnitude is 10 newtons. I'm just pulling numbers out of the air, and calculate the acceleration by taking the force, the net force, divided by the mass, which is 10 newtons, divided by 3 kilograms, which is 3.3 meters per second squared. So now what we're going to do is change these masses. I chose 3 kilograms. Why? I just wanted a number. It says the mass increases by a factor of 4. That means the new mass is going to be 12 kilograms. I chose 10 newtons as a force, and it says the net force decreases by a factor of 4, so that would mean 10 newtons divided by 4 is 2.5 newtons. And then I can grab my calculator and take that net force of 2.5 newtons, the new net force, and divide by the new mass of 12 kilograms, and I get 0.2083333, and that's the new acceleration. If I divide that by the old acceleration of 3.33333, and then I convert that to a fraction, I can see I get 1/16. So there is a way to do this type of question by choosing numbers. If the mass decreases by a factor of 4 and the net force is 0, well, if the net force is 0, then the acceleration will be 0. Kind of a trick question. The acceleration reduces to 0 meters per second squared because there's no net force. All right, we have a couple more very quick questions to do. But I would like to talk about the units of force and how this equation all works. In physics, there are things called fundamental or defined units. For example, the kilogram is a fundamental unit. The kilogram is defined in a particular way. Up until recently, it was defined as the mass of a particular piece of metal that's stored in France. The meter was also defined in a similar way. The second is defined in a similar way. And although I know for you physics buffs out there, you're going to cringe at me saying this, I'm going to say it anyway because it works best in high school to think this way. The coulomb is a standard unit. I know that a coulomb is not technically a standard unit, but this works best for high school students. Okay, there are a couple of others, but we're not going to worry about them. It turns out that everything we deal with in high school physics can be written using combinations of these. So for example, derived units are things like volts, joules, amps, newtons, Tesla, there's a unit called the Tesla. These are all derived units. So let's take a look at Newton's second law of motion. F net equals MA, and I'm not worried about the directions, so I'm just going to use the magnitudes. And when we take a mass of, say, it doesn't matter, I'll take 2 kilograms multiplied by 3 meters per second squared, what we get for the net force, we get F net is equal to 6, and the units are kilogram meter per second squared. And up until quite recently, you know what, I want to say the 1960s, and I know the 1960s in your mind is a long time ago, but Newton lived in the 1600s. So 1960 is very recent in terms of physics. Up until the 1960s, that was the set of units we used for force, kilogram meter per second squared. And somebody decided, I don't know the history behind it, you can look it up yourself, that rather than writing kilogram meter per second all the time, what we can do is we can define that set of units to be something which we call a Newton in commemoration of Isaac Newton. So I mentioned that because by the time you get to Physics 30, we'll be doing more unit analysis. And I also want you to know why kilograms times meters per second squared gives you newtons. It's because we say it does. A kilogram times a meter per second squared is a newton. And by the time you get to Physics 30, you will learn things like an amp is a coulomb per second. A volt is a kilogram meter squared per coulomb second squared, etc. There are a variety of unit combinations that you will become more familiar with. Let's take a look at the final two examples. A lacrosse player exerts an average net horizontal force on a ball of 2.8 newtons forward, and the ball's mass is given. What is the average horizontal acceleration? Well, acceleration equals net force. Divided by mass. We're going to include the direction, but I don't like including the direction in the formula. So what are we going to have here? We're going to have for the magnitude of the acceleration 2.8 newtons. 2.8 newtons divided by 0.14 kilograms. By my count, that works out to, I better check it with a calculator just to make sure. I wanted to say 20, but my brain is just not braining right now. I'm pretty sure that's right. Whoops. Yep, 20 meters per second squared. It's meters per second squared because a newton over a kilogram is the same as a kilogram times a meter per second squared over a kilogram. So what happens is the kilograms cancel. And then we can put the direction on there. The direction of the net force was forward. So the direction of the acceleration is forward. Really a straightforward question. This is a Science 10 question. Without all the vector symbols in that, it would have been something in Science 10. And the final example, two athletes are on a team. The two athletes are A and B, Albert and Bernie, and they're practicing to compete in a canoe race. Athlete A has a mass of 70 kilograms, B has a mass of 75, and the canoe's mass is 20 kilograms. A exerts an average force forward of 400 newtons on the canoe. So there's a force forward on the canoe of 400 newtons because of athlete A. There's also a force forward on the canoe of 420 newtons because of athlete B. Let me put in those numbers. (400 newtons), 420 newtons, and it says, during paddling, the magnitude of the water resistance on the canoe is 380 newtons. just to stop for a second, I hope you can imagine that if you had a way of applying these forward forces to the canoe on water, and then you had a way of somehow, I don't know how, applying the same forward forces to the canoe if it were on a sheet of ice, the acceleration on the ice would be greater. So there's something going on between the canoe and the water that is taking away from the force forward. And we're calling that a resistive force. And it is 380 newtons, so I'm going to draw that force in. And what we've drawn is a free body diagram, which takes us back to unit 1. Sorry, lesson 1. So this is 380 newtons. Do that again, 380 newtons. So what is the acceleration? It's the net force divided by the mass. Well, what is the net force? The net force is the sum of all of those forces. This is not a difficult calculation. We're going to take the 400 newtons, we're going to add the 420 newtons, and we're going to take away the 380 newtons because we're adding vectors that are in opposite directions. We have to assign a negative to the one on the left because it's going to the left. You know, it's not that it's going to the left, it's opposite to the direction of the other forces. So we add those together, what do we get? 820, I believe it's going to be 540, but again, why take a chance? There we go, 440. I think I said 540, so yeah, I was wrong. 440 newtons, just double check that, looks okay. So the acceleration, I normally don't like writing equals equals, but I'm crushed for space here, so I'm going to do that. 440 newtons divided by the mass. Well, it's not just the mass of athlete A that's accelerating, and it's not just the mass of athlete B, and it's not just the mass of the canoe. It's the total mass, which is 70 kilograms plus 75 kilograms. Plus the 20 kilograms, I think, of the canoe. Mass is a scalar, so when you're finding a total, you just add the numbers together. That's 165 kilograms. I'm pretty sure about that, but I'm going to check anyway. 75 plus 70 plus 20 is 165. All we're going to do now is take 440 newtons and divide it by 165 kilograms, and I get approximately 2.7 meters per second squared in the direction that they are rowing. Which in my diagram is to the right, so I'll just put right for a direction. At the beginning of this lesson, I said that we're going to be looking at applications of Newton's second law. This is a very basic one where you have these three forces. You will see as time goes on that it isn't necessarily that the numbers of forces will increase, but the directions or the complexity of what's going on will be greater. So I hope that made sense. There is an assignment attached to this. You can work on those problems, and we'll talk to you all later. Take care.